Welcome back to the Machine Learning Mastery playlist. I am thrilled to have you here today because we are able to embark a journey into the powerful world of gradient boosting. Get ready to uncover the secrets of this game-changing technique and elevate your machine learning skills to the new heights. I am Bhaskar, and in this video, our goal is to demystify gradient boosting and explore its application in boosting ensemble models. Whether you are a beginner or have some experience with machine learning, this video will be a guide to provide you with easy and step-by-step guidance. Gradient boosting is an incredibly important algorithm in the field of machine learning. It's known for its ability to significantly enhance the performance of ensemble models. In this video, we will break down the concepts, implementation, and practical tips surrounding gradient boosting. By the end, you will have a solid grasp of this technique and be able to apply it confidently in your own projects. Let's dive in. We will start by understanding the core principles of gradient boosting and its role in boosting ensemble models. Then we will move on to the implementation details, covering step-by-step process and important considerations. Finally, we will explore the practical tips and real-world applications to demonstrate the power of gradient boosting. So, without further, let's get started. Understanding gradient boosting. To understand the gradient boosting, we first need to grasp the concept of ensemble learning. What is ensemble learning? An ensemble learning involves combining multiple models to make better predictions than a single expert model. Gradient boosting takes this idea a step further by building models sequentially, with each model correcting the mistakes of previous ones. In gradient boosting, we will work with weak learners, which are models that perform slightly better than random guessing. These weak learners are trained to capture the patterns that previous models couldn't handle properly. The key optimization technique in gradient boosting is gradient descent. We use this algorithm to minimize the loss function guiding the creation of subsequent models. Loss function or objective function is the function we want to optimize in the model creation. So in any model, we will having a loss function which we want to optimize it. Gradient descent enables to find the direction of the steepest descent in the model's parameter space. So what is gradient descent? Let's see with an example. So this will be our curve, or which we call it as loss function or objective function, and our main objective is to move in this direction. Wherever the points, it can be here, 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 anywhere, we should reach the bottom. Because if you see the x-axis, y-axis, this will be our bottom part. So we want to move this. So with the help of gradient descent, we will be moving in this downward direction and taking steps. It's like taking one step at a time. So if you are here, then it will be like this. So that's what gradient descent is all about. So we are moving in the downward direction of a valley. Implementation of gradient boosting. Now that we understand the core principles, let's explore how to implement gradient boosting. The process involves several steps, and I will guide you through each one. Gradient descent is used to update the model at each step or stage. Learning rate determines our steps. That is, how quickly we can move, which determines the impact of each new model or ensemble. Finding the right balance is crucial for achieving convergence and optimal performance. Regularization techniques like shrinkage and subsampling play a vital role in gradient boosting. Shrinkage, also known as regularization or weight decay. It is a technique used in machine learning to prevent overfitting and improve the generalization performance of the new models. The concept of shrinkage involves introducing a penalty to the objective function during model training. This penalty term discourages the model from assigning excessively high weights to the individual features or decision rules. So basically, in objective function, we are just trying to add a penalty term which penalizes the model if there are more weights. One more technique is subsampling, also known as stochastic gradient boosting or random sampling. It involves randomly selecting a subset of data points or features during the training process, just like a random forest. The main idea behind subsampling is to introduce the randomness in the model training, which helps prevent overfitting and enhances the generalizability of the model. There are two common types of subsampling used in gradient boosting. One is row subsampling, also called as sample subsampling. So in row subsampling, a random sample of training data set is used for each training iteration. So we're just randomizing the samples, rows. Whereas in the column subsampling, a random set of features is used for each iteration of the gradient boosting process. This means that when training a weak neuron at a particular node of decision tree, only a subset of available features is considered for splitting. Feature subsampling adds further diversity to the ensemble of weak neurons by limiting the number of features available at each split. The model avoids becoming overly reliant on any simple feature and encourages a more balanced representation of input space. This can also help to reduce variance and make the model more robust. They help control the complexity of the model and prevent overfitting. By applying these techniques, we strike a balance between accuracy and generalization. In gradient boosting, three-weighted models such as decision trees are commonly used as weak neural. Decision trees provide a flexible framework for capturing complex relationships between the data. So, as you know, it's the gradient boosting. We're trying to correct the mistakes of previous model in each iterations, right? So we need a weak model. So we can simply take a distance stamp or distance tree. That will be our weak model. So on top of it, we're trying to build a gradient distance in it. Section 3. Practical tips and applications of gradient boosting. Now that we have solid understanding of gradient boosting, let's explore some practical tips and real-world applications. Hyperparameter tuning in gradient boosting is a crucial step to optimize the performance of the model. Since gradient boosting algorithms have several hyperparameters that control learning process and model complexity, tuning these hyperparameters can significantly impact the model's accuracy and generalizability. So, here are the key hyperparameters commonly tuned in gradient boosting. One is learning rate. Can also be known as shrinkage rate or step size. It controls the contribution of each tree to the final ensemble. A small learning rate reduces the impact of individual trees, requiring more trees to build a strong model. So if learning rate is higher, we need less number of iterations. It's just a balance number of trees. The number of trees or bushing rounds represents the total number of weak learners to be sequentially added to the ensemble. A higher number of trees can improve the model performance, but it also increases the computational time. It is essential to find the right balance between the accuracy and efficiency. Next is maximum tree depth. Each inventory, the how much max it can go. That means, for example, if you have a tree like this, so here level 0, I mean depth 0, depth 1, depth 2. So each inventory what is the maximum depth. If we shop it here, it will be maximum depth equal to 2, right? Yes. Next, minimum samples per leaf. This hyperparameter sets the minimum number of samples required to be at leaf node. Setting higher value can prevent the tree from splitting nodes with very few samples, contributing to more robust trees and reducing overfitting. So, as you already aware in the decision tree, if we if we don't set it, it will keep on building till we get one sample, which is kind of overfitting. So, in order to prevent it, we need to set the minimum samples per leaf. Next is subsampling parameters. As mentioned earlier, subsampling techniques like row subsampling, column subsampling can be used for it. Regularization parameters. Some gradient boosting algorithms like XGBoost have additional regularization parameters such as L1 and L2. So L1 and L2, I think we are already familiar, right? Lasso L bridge. So we are just adding it to the objective function. Other hyperparameters. Other hyperparameters may include subsampling rate for gradient updates, such as minimum child weight, scale post weight for imbalanced datasets. The importance of these parameters varies depending on the specific algorithm. To tune the hyperparameters effectively, things like grid search, random search, or Bayesian optimization can be employed. Cross-validation is crucial to evaluate the model's performance on different parameters combining and select the optimum set of hyperparameters. One of the key advantages of gradient boosting is its ability to provide insights into the feature importance. So we can have feature importance at the end of the model. Advantages of gradient boosting. High accuracy. Gradient boosting algorithms such as XGBoost, Lysium are known for their high accuracy and predictive power. They can offer outperform other machine learning algorithms on a wide variety of tasks. Ensemble of weak learners. Gradient boosting combines multiple weak learners to form a strong ensemble model. This approach helps reduce the bias and variance. Handling nonlinear relationships. Gradient boosting can effectively model complex and nonlinear relationships between the features and target variable, making it suitable for a wide variety of real-world applications. Feature importance. You can get a feature importance of each feature. Robustness to the outliers. Gradient boosting algorithms are robust to outliers and noisy data. Outliers have less impact on the final predictions due to the aggregation of multiple models in XGBoost or in gradient boosting. Handling missing values. It can handle missing data without the need for imputation. Disadvantages of gradient boosting. Computational complexity. Gradient boosting can be computationally expensive, especially when dealing with large number of features and a high number of trees. Hyperparameter tuning. Gradient boosting algorithms have several hyperparameters that require tuning for optimum performance. Finding the right combination of hyperparameter can be time consuming and requires cross validation. Overfitting. Gradient boosting has the potential to overfit the training data, especially when the model is too complex or the number of trees is too large. Proper regularization and hyperparameter tuning are essential to prevent the overfitting. Black box nature. Like any other ensemble models, gradient boosting can be considered as a black box model. This interpretability of the model's predictions can be challenging, especially when dealing with large number of trees. Less effective on small data sets. Yes, gradient boosting may not perform well on small data sets due to the risk of overfitting. In such cases, we can use simple models or data augmentation. Add more data. Long training time. The time taken to train a gradient boosting model can be longer compared to the simple algorithms like linear regression or decision trees. This can be a limitation when real-time predictions are required. Despite these disadvantages, gradient boosting remains a powerful and widely used algorithm in the field of machine learning due to its exceptional predictive performance and versatility. Properly understanding and tuning the hyperparameter can help harness its strengths while mitigating its limitations. Lastly, there are recent advancements and extensions of gradient boosting such as XGBoost and LightGBM, which we have already discussed. These frameworks provide additional features and improvements that can further enhance your models. Congratulations on making it through this entire video. By now, you have a solid foundation of gradient boosting and its applications in boosting ensemble models. I encourage you to apply gradient boosting in your own machine learning projects. Its versatility and effectiveness make it a valuable tool in your toolkit. If you are hungry for more knowledge and want to explore advanced algorithms and techniques, be sure to check out other videos in the Machine Learning Mastery playlist. We have got plenty of exciting content waiting for you. Before we wrap up, I would like to ask for your support. Please like, subscribe, and share this video with others who might find it useful. Your support helps us grow and create more valuable content. Thank you for joining me today. I appreciate your time and enthusiasm in learning about gradient boosting. Keep mastering machine learning, and I will see you in the next video. Thank you.